You know, in the story of modern economics, you have people who come up with these big, grand theories. And then you have the architects, the people who build the tools that let us actually test if those theories are right. Today, we're talking about one of the great architects.
So let's start with a really big question. Just think about it for a second. How do you test a theory about the entire economy when you can't possibly build a perfect model of it? I mean, it's a huge problem, right? How can you tell if your brilliant idea about how markets work is actually true if testing it means you need to know every single moving part of the global economy? Well, this was the puzzle that was staring an entire generation of economists right in the face.
So let's set the scene. We're going back to the 1970s, a time that really highlights what we're calling the economist's dilemma.
Okay, so there was this incredible tension in the field back then. On one hand, you had these powerful, elegant new theories popping up, like the Consumption Capital Asset Pricing Model, the CCAPM. I mean, these were genius attempts to link our daily decisions, what we buy, what we save, to the massive swings of the financial markets. But, and this is a huge but, on the other side, the demands for testing them were just impossible. To statistically test these models with the tools they had, you had to literally specify the entire joint probability distribution of the economy. That means knowing every variable, every possible shock, and how they all relate to each other. It was an absolutely impossible task.
So economists were completely stuck. Imagine this. You've invented a revolutionary new spark plug for a car. But to test it, the rules say you first have to design and build the entire car from scratch. The engine, the transmission, everything. That's what it was like. To test one little piece of a theory, you had to model the whole world first, and it was seriously holding the entire field back.
But right into the middle of this frustrating problem steps a young economist named Lars Hansen. And he didn't try to solve the old problem. He reframed it by asking a totally revolutionary question.
And you can hear it right here in his own words from his Nobel Prize interview. He said, "I did work that I think of in a very simple way as trying to show how you can do analysis without having to do everything." Listen to that again, without having to do everything. That really simple, incredibly elegant idea, that's the key to this whole story.
And that was the huge shift in perspective. Everyone else was asking, how can we possibly build a perfect model of the entire economy to test our idea? But Hansen's question was completely different. He asked, what if we don't have to? What if we could test a theory by focusing only on its most essential claims? Forget building the whole car, let's just test the spark plug.
And this incredible shift in thinking led directly to one of the most important methodological breakthroughs in all of modern economics. We're talking about the GMM breakthrough.
And this brings us to the hero of our story, the Generalized Method of Moments, or GMM, which Hansen introduced in a groundbreaking paper in 1982. So what is it? Well, it's a statistical method that lets you estimate and test your models based only on their core rules, what economists call moment conditions. And here's the kicker, without having to specify everything else about the economy. It's the toolkit that finally lets you test the spark plug without building the whole car. So how on earth does it work? Well, the logic is just so elegant. Most economic theories make predictions about relationships that should, on average, hold true in the real world. So, step one, you just identify one of these core rules your theory predicts. A classic example is an equilibrium condition, some kind of balance the theory says should exist. Step two, you go look at the actual data and see if on average it follows that rule. And step three, this is the really genius part. You take any deviation from that rule, any mismatch, and you use it to estimate the model's parameters and formally test if the theory actually holds up. It's targeted, it's powerful, and it's incredibly efficient.
Now this is the math at the heart of GMM. But don't worry, you absolutely do not need to be a statistician to get the big idea. This E just stands for expectation, or the average. So the equation is basically saying that, according to your theory, some relationship in the data, this little m function, should equal 0 on average. That's a moment condition. GMM is really just a powerful machine for checking if the real-world data actually backs up that claim.
Now, to really unleash this amazing new tool on the world of finance, Hansen and his colleagues reframed asset pricing around this beautiful unifying concept, the stochastic discount factor, or SDF. You can think of the SDF as like a universal translator for finance. It's a way of representing how all of us, as investors, value future money based on when we get it and how risky it is. And the beauty of it is that pretty much any rule from any asset pricing model, once you write it in the language of the SDF, turns into one of those moment conditions, the exact kind of thing GMM was built to test.
So, Hansen had built the tool. And in doing so, he basically created a whole new empirical architecture for the field of economics.
And this timeline just shows you how revolutionary this was. So in the 70s, you've got the CCAPM theory. It's brilliant, but it's basically untestable. Then, in 1981, Robert Shiller, who would actually share the Nobel Prize with Hansen decades later, he presents this evidence for excess volatility, arguing that stock prices just seem to move way too much to be rational. But his methods were a bit informal. Then boom, 1982, Hansen publishes his GMM paper. And in the years that followed, a whole wave of researchers used GMM to formally test these ideas, and they ended up confirming Shiller's findings and decisively rejecting the simple version of the CCAPM. It was like a seismic event in finance.
This was a total paradigm shift. I mean, for the first time ever, researchers had a really robust statistical toolkit. They could move beyond just telling stories or using informal arguments. They could now stand up and formally reject even the most powerful, elegant theories with actual, hard, empirical discipline.
And all of this new rigor also shone a bright light on a really tricky fundamental challenge in finance, something called the joint hypothesis problem. Hansen's work made it crystal clear that anytime you test if markets are efficient, you're always testing two things at once. You're testing market efficiency, and you're testing the specific model of risk you're using. So if your test fails, what does that mean? Does it mean markets are irrational, or could it just mean your theory of risk is wrong? GMM forced economists to stare that question right in the face.
And all of this work together is what cements Hansen's enduring legacy as just a foundational figure in all of economics.
You can really think of it as the Hansen rupture, the moment the ground completely shifted. He gave the field the tools for real discipline. He helped unify all those different asset pricing models under the single framework of the STF. He clarified that super tricky joint hypothesis problem. He truly helped integrate macroeconomics and finance. And of course, GMM became a standard go-to tool, not just in finance, but in basically every corner of economics.
When you get right down to it, Lars Peter Hansen built the empirical architecture, the very foundation that almost all of modern financial economics is built on today. He didn't just give us a new theory. He gave the entire field the tools to build and test all theories with a level of rigor they never had before.
And that leaves us with a really fascinating final question. Hansen gave us these incredible tools to test our models against the data. But what happens when we're uncertain about the models themselves? What tools do we need when we know that our simplified views of the world are, well, incomplete? That very question is what would drive the next phase of his Nobel-winning research. And honestly, it's a question economists are still wrestling with today.